Okay guys, today we're going to be learning about summations. So I know that this is going to be a new topic to you, just like everything in this unit is, but this isn't really changing anything about our sequences. All we're going to do is just start adding the numbers in those sequences, and that's it. So we're just going to be taking a sequence like this and add them all together, or a sequence like this and add them all together. But in order to start doing that, we need to learn about the notation for what a summation is. So this is called a sigma. Sigma is the symbol that notes that we are about to add together all of these things. So when we put a symbol like this here, what we're saying is we're going to be summing everything in some function. So we're going to be using this function, a of n. And we're going to sum together a bunch of terms in a of n. So let's say that I wanted to put together terms 3 through 5. What I would do is I would say start at 3, finish at 5, and add those terms together, right? Or I could, let me erase that. If I wanted to do terms 1 through 10, I could just say 1 to 10, and now I know that in this sequence, what I'm going to do is find the first 10 terms, and then I'll just add them all together. I don't want the 11th term. I'm just going to go 1 through 10 and add them all. So that's all this is. So let me just kind of label this here for you in a more generalized form. Get rid of this. All right, let's say n equals x. I'd use a, but a is the name of the function, so that would be a little confusing. So from x to b, where x is our first term, b is our last term, and a of n is the sequence used. So that's all that this is. We're just going to be adding together a bunch of terms, and you're going to start seeing that notation. So consider the following sequence, a of n. It equals 3 times n plus 1. So obviously this is a sequence in explicit notation. I don't see a definition for the first term. I don't need it, because this isn't telling me that I need the term before it. So it'll be pretty easy to find what we need. If I want to add all that together, what that's going to look like is a summation of a of n from 1 to 3, because it's saying to find the first 3 terms in the sequence and add them together. So let's figure out what those are. A of 1, a of 2, a of 3. By now, you guys should be able to evaluate these pretty easily, so I'll skip through that part. Okay, so we have to just add all these things together, and we get 21. So the summation of a of n from n equals 1 to 3 is 21. Okay, it's as easy as that. So I'm going to be giving you a function. In here, the function is defined, so I can put a of n here, but sometimes we'll just leave the function hanging here, like you'll see in the next couple examples. So calculate the summation of this function given here, which is just 3 times whatever I is. In this case, I is not an imaginary number. It's not the square root of -1, because they've defined I to be 2. So in this case, we're using it as a variable. This is something you'll see often when we deal with sequences. I is not often an imaginary number, although if I is just placed in there and not defined, then it is an imaginary number. So here they're saying I equals 2. Let's just make a note that that's a common thing. So if I'm going to add all these things together, then that means I need the second term, the third term, the fourth term, and the 5th term of the sequence. Notice I'm not starting at 1, because it says to begin by plugging in a 2 for I. And we could evaluate this pretty easily. Okay, and once we've evaluated each of those, we just have to add them together, and we get 42. The second example is the summation from k equaling -2 to 2 when 1 is to the k power. So remember, this is okay. I remember talking about sequences where we said that the first term is the lowest term we can go with, right? The only inputs we can have for these sequences is going to be positive whole numbers. This is okay because all we're going to do is use this k to find the first term. So we still are trying to find the first term, but we're using a -2 to find it. Might be a little confusing, but it's okay because you'll see that the first term is still just the first term, regardless of how we get there. So this says we've got to plug in a -2, a -1, a 0, don't forget 0, a 1, and a 2 to find each of the terms of the sequence. So when I do 1 to the -2nd power, that's going to be 1 over 1 squared. Remember what the negative exponents do. But that just ends up being 1 over 1, which is 1. When I do 1 to the -1st, that's the same as 1 over 1 to the 1st, which is just 1 over 1, which is 1. 1 to the 0 power, well, anything to the 0 power is 1. 1 to the 1st is obviously 1, and 1 to the 2nd, still just 1. Remember, 1 to any power is going to give you 1. So I'm going to add those all up, and I should get 5. That's a little practice in dealing with some negative exponents. All right. The last thing we're going to do here is I'm going to give you the sequence, and you just have to represent this sequence as a sum. So you need to use sigma, you need to tell me what variables to use, and you need to give me the function. You need to tell me what's happening here too. So in this first sequence, it looks like every number is just being added by 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's how I'm going to go about doing this. I'm going to say, well, if the common difference between each of my numbers is 1 times plus 1, plus 1, plus 1, then that means whatever my variable is that I'm going to be using, which is I, has to be multiplied by 1. So I'm going to have a 1 times I. So let's check and see if this works. If I plug in a 1 to this function, I will get 1 times 1, which is 1. If I plug in a 2 to this function, I will get 1 times 2, which is 2. If I plug in a 3, I'll get 3. If I plug in a 4, I'll get 4, and so on. So this is a pretty basic function because I can just plug any number I want into it, and that is exactly the number that comes out of it. I don't even have to put this 1 here, right? I could just say, I don't need that 1, and it's just I. Makes no difference. Okay, so I've got my function. I'm going to be summing some number of terms of this function, and I need 1 through 10. So in order to get 1 through 10, my first term is going to have to be 1. My last term is going to have to be 10. So this is a summation that would work. There are an infinite number of other summations that would work. So don't think that that's the only correct answer. Like for example, if I put this, and I use this function, I plus 1, this would work too as long as my first term is 0 and my last term is 9, right? All I've done is I've just shifted the way that I'm going to calculate these numbers. If I plug in a 0 here, I get 0 plus 1. That's my first term. If I plug in a 1, I get 1 plus 1. That's 2. That's my second term, right? So this would also model this same sequence. It doesn't matter. They're equal. There are a lot of different ways that you could write these. So don't think that there's only one way. The last one. This sequence is a little bit trickier to identify. So what we've got going on here is we've got a 4 becoming an 8 becoming a 16 becoming something, and then a 10, 24. So what is happening here? Well, it seems like that's times 2, that's times 2. If I keep going like this, I'll eventually get times 2 to 1024. So all I know right now is that 2 is being multiplied by itself some number of times, right? That's what I see here, times 2, times 2, times 2, times 2. But we don't know how many times. Well, it's an unknown number, and in this case, we're using I to represent that unknown number. So our function could be 2 to the I power, meaning I'm going to multiply 2 by itself, I number of times, to get to whatever term I need to get. Well, I'm summing my first some number of terms, however many will get me to 1024. But remember, I can't use a 1 to begin this. If I start here at 1, what will happen? Well, 2 to the first power equals 2. Notice, that is not our first term. So I can't begin at 1. I have to begin at whatever number is going to give me my first term. So I'm going to start this summation at 2. 2 times 2 is 4. So then I would do the next one, which would be 2 to the third, which would be 8. 2 to the fourth would be 16. 2 to the fifth, sixth, seventh, eighth, and actually 2 to the ninth is what would give me 1,024. So I've figured out that I need to go from 2 to 9 if I want to represent this sum. Again, there are other ways to write this sum, but this is the easiest way, I think. All right? So summations are just a continuation of these sequences. We're still identifying sequences, trying to come up with functions to model these sequences, but now all we're doing is we're just adding a set number of terms of those sequences. All right? I'll see you guys tomorrow.